so far all of our trees have been pretty, and so it's been easy to visualize this, but these aren't all pretty trees. These trees all have the letters A through G. They all have the same letters, but they all have different heights. And they all honor the binary search tree. No, they don't. They're not binary search trees. They're just binary trees. Okay. So in this case, what level is node F? 3. So what's the height of this tree?
3.
Right, because the max level is 3. F, G, D, and E all have that same level. In this case, what's the max height? 5. I mean max level. 5. So the height of that tree is 5. Even though we've got these little stubbies over here, this is what dominates the height of the tree. What about this guy that zigzags all over the place? 7. And it doesn't matter that it zigzags. It's level 1, 2, 3, 4, 5, 6, 7. And so this is a level 7 tree. This is actually the same. I was wrong. They're different. So this is 1, 2, 3, 4, 5, 6, 7. 7 is my max, and this is also the level. Now, is this actually a tree?
No.
Yeah, not a helpful one.
So what's the definition of a tree? We have a root, and then all of the people below it are trees, all the children below it, right? So if this is my root, is everything below that a tree?
Yes.
Well, it actually is. So you could get all the way down to here, say, here's my root, that's a tree, just a leaf node. So this is in fact a tree. It's a special kind of tree, we call it a vine, because it isn't very useful. And we actually want to avoid vines because it looks an awful lot like a list. And so we lost all of the benefit that you don't even know about yet, but we lost all the tree benefits by making it a vine. Yeah.
Is C also a vine?
Yes, but it's a twisty vine.
A twisty vine. Oh.
But it
Is
doesn't.
that a technical term?
No. It doesn't make any difference that it's a twisty vine. It's still bad.
Okay.
But this is the kind of vine that you actually end up seeing. Usually it's from some poor programming practices. I don't know if I've ever seen one of these. But definitely, when we get to some of our traversals, I'll give you a story of how I ended up with one of these one time by accident. Okay, so far so good on height, level, all that stuff, right? So now we're going to talk about full, complete, and balanced binary trees. 3 different concepts. This is a full tree. It's pretty intuitive. What's that? Yes. We'll get to balance in a bit. It's pretty intuitive when you look at this and I say, all right, where could I add another node without increasing the height of this tree? Nowhere, right? So I can't add another node anywhere. This tree is full. In order to add anything, I'd have to increase the height. Okay? So definition, the technical definition, the tree is full if it's empty. So if a tree is empty, it's full with a height of 0. If it's not empty, it has a height greater than 0, and all of its subtrees are full. Well, the subtrees are full with the height of each minus 1. So again, here, I know this is full because it's not empty. And if I start this root, both of these subtrees are full. And I can check and say, well, are you full? I don't know, ask my node. My node says, yes, I'm full, I don't have any children, and so on. And so that whole says, I'm a full tree, I'm a full tree, oh, I must be a full tree. And he comes up and says, I'm full. And this same guy, this guy says, I'm full, I must be full. Both the children say they're full, I must be full. So that's the definition. It's a little more technical when you go through the definition. Intuitively, it's pretty obvious. When you see a binary tree, it's full. It's a triangle. All right, this one, is this tree full?
No.
No, it's not full because there's spaces over here. But this is a complete tree. So a complete tree, well, what's the height of this tree? 5, because I have, well, what level is this node? 4. These are all 4s, and what level are these? 5s. So the height of the tree is the maximum node height. My maximum node height is 5. Okay? So the definition of a complete tree of height n is it's full at n minus 1, and then at level n, it is filled from left to right. Now that's somewhat arbitrary. We could have gone the other direction, but this is just the definition that I've always seen. Maybe someone defines it the other way, I don't know. But this is the complete tree. We'll see later why we care about calling something a complete tree, but we're all good with that so far, right? And we didn't talk about balanced. It doesn't come back. Let me cover that real quick. A balanced tree is, well, our full tree was balanced. And I mean, balanced, if you think intuitively, that means it's not a vine, right? Everything is basically about the same. That's the intuitive definition. The actual definition is there does not exist two nodes in the tree, two leaf nodes in the tree whose height differs by more than 1. So this would be considered balanced because I have a 4 and a 5, so that's only 1 off. But if this node was missing, if both these nodes were missing, I'd have a leaf of 3, a leaf of 4, a leaf of 5, but the 3 and the 5 would be separated by more than 1, so this would not be considered balanced.
Quick question on complete. So the second part you said is that it's filled from left to right.
Did I get my stuff? Yeah.
And then the first part, just so I understand it, you were saying that something about n minus 1, so if n is the height, the n minus 1 is completely filled out.
Yeah. So with a tree of height n, in this case n is 5, a full or complete tree is full to n minus 1, so full at 4. And then at level 5, it's filled from left to right. Okay? Now we're going to talk about our max and minimum heights for binary trees. Don't really like this diagram because it doesn't really fit what we're saying here, but we'll get to it. The maximum height of an n-node binary tree is n. I mean, it's true because I said it here, but you believe it. Yeah, so that's our vine, right? That's just a vine of just this, all the way down. That's not a very nice tree, but it is a tree. Okay? Again, I don't quite realize where I put this in here. So, let's count some nodes in trees. We're going to now talk about the minimum. The max is easy. Max is the number of nodes just for multiplying. What about the minimum? How can we get there? Well, let's notice some properties here. If I have one node, it's only at one level, I can only store one node there, right? So this is, the number of nodes at this level is 2 to the 0th. Then at the second level, how many nodes can I have at level 2?
2.
2.
2 children.
Right, 2 children of level 1. So I can have 2, so I get 2 to the first power, so 2. Now, when I go to the third level, each of my parents can have 2 children. So I'm multiplying times 2 again, so the total number I can have here at level 3 is 2 to the third, or 2 to the second. 2 to the second, yeah, sorry. I'm getting that, I'm just with that one. Okay. So I can get 4 here. And then I can double down here, so I can get 8, and so on, and keep doubling. So at the height h, I have 2 to the h minus 1 nodes possible on that level. Now, this is just the number of nodes at that level. I want to know the total number of nodes at that level in all previous levels. So at the first level, it's easy. It's 2 to the first, it's 1. If I only have a 1-level tree, binary tree, it's only got 1 node in it. If I have a 2-level tree, it's got how many nodes?
3.
3. And then here I get 7, and so on. So I get 3, and 3 is the next level, minus 1. So it's 2 squared minus 1. So at level 2, the maximum number of nodes my tree can hold is 2 to the 2 minus 1. At level 3, it's 2 to the 3 minus 1, and so on. So at level h, it's 2 to the h minus 1. Not to be confused with 2 to the h minus 1. Right? So,
2 to the h minus 1, not to be confused with 2 to the h minus 1.
right.
Got
So it depends on how you say it. But it's a big difference. So the maximum number of nodes you can hold in a tree at level 8 is 2 to the h minus 1. And this is the value that's actually more important. This one we don't use as much, the number of nodes at a level. Don't care so much about that. This is the one that you should remember the most. Okay, so we got that. So just like Pox quiz, if I have 5 levels, how many nodes can I hold in a 5-level binary tree?
16.
It's not 9 and it's not 16.
Wait, first off, level 5, 32 minus 1, 31.
Oh wait, that would be
2 to the 5th is 32. Minus 1 is 31. Yeah, so there we get there. 31. So if I have a tree that's 5 levels deep, I can hold 31 nodes in that tree. Is that? It's math, I know. Okay. Full binary trees. A full binary tree of height h more than 0 can hold then 2 to the h minus 1 nodes. We just go through that. Also, you cannot add nodes to a full binary tree without increasing the height. Again, this is our intuition coming to the rescue, right? Here's a full tree. Where would I add another node? It's got to be down. I can't just hang it off here because that's not binary anymore. So if I want to add nodes to a full binary tree, I'm going to add the height. The maximum number of nodes that a binary tree of height h can have is 2 to the h minus 1. Same thing here. Now, this is where it gets a little tricky. The minimum height of a binary tree within nodes is log base 2 of n plus 1. So this is kind of the inverse of doing this function.
It is the inverse.
It is the inverse, for those of you who are really good on your math. For everyone else, it's still the inverse too. You just might not recognize it. But so if I have, let's say it was down here. Well, in this case, I have 15 nodes. The minimum height is log base 2 of n plus 1. Now you can get there intuitively again. You can get there by, remember what I described about log base 2, right? Log base 2 of a number is, do you guys remember how I described it? Has something to do with dividing in half. Yeah, how many times can you divide it in half until you're down to 0, right? And so we're doing the same thing here. I've got 15 nodes. I'm going to add 1 and make it 16. And now how many times can I divide that in half until I get down just to the 1? So I can do that 4 times. And so, in fact, 4 levels is what I can support. And now why am I dividing in half? Well, if I go from here to here, how many nodes do I cut my number of nodes in half. Start with this, cut it in half, cut it in half, cut it in half, right? So this log base 2 thing is going to come up a lot anytime we're dealing with binary trees and binary stuff, because you're just dividing things in half a lot of times. Same thing with powers of 2, except you're multiplying. So the minimum height of a binary tree within nodes is this. Log base 2 of n plus 1. So that is also important, because that way if you're given some value n, you can determine, without actually making the tree, you can determine how deep the tree is going to be. I mean, best case. And you can't do any better than that either. You can't make this tree more optimized for 15 nodes. That's as best as it gets. Okay, this is doing the complete tree where we just fill it in. Another slide I didn't make sense of. All right. Are we good so far with those definitions? Because now we're going to turn to a new concept with trees, and it's called traversals. Okay. I started out